Hello and welcome to A-level chemistry online. This video is part of Unit 1, Atoms and Bonding. And the subject of this video is Mass Spectrometry and how to solve problems involving isotopic abundance. So during the course of this video, we're going to look at how mass spectrometers work, how they're constructed and how they work. And two, we will look at some questions that might be asked in an exam context. And how these might be answered. What is a mass spectrum? Mass spectrum shows the abundance of different ions and their masses in a mixture that exists within a mass spectrometer. This might seem long-winded, but it is quite reasonable to inject a pure sample of something into the mass spectrometer, consisting of particles of one size, and still get a spectrum showing a diverse mixture of particle sizes. In this case, the mixture is forming from the single species being injected inside the spectrometer. A mass spectrum might look something like this. On the horizontal axis is a scale representing increasing atomic mass, or mass charge, m over z. On the vertical axis we have the intensity, that is the amount of these ions making it to the detector of the spectrometer. It's a kind of frequency histogram. The MS I have shown gives absolute intensities. However, this information may be represented as relative intensities, where if you sum the total number of particles hitting the spectrometer detector and define this as 1 or 100%, the peaks will be given as fractions or percentages of the whole value. Of course, you could just sum the peaks of interest and quote the results in terms of fractions or percentages. This spectrum is from a compound I actually made in the lab many years ago. The relative molecular mass of this compound is 510.2. We will call this compound M for mother, it being the mother of any ions produced. The sample is ionized by electrospray ionization, which we will discuss later. This gives a peak at 511.24, which represents M plus H plus. The other two main peaks, here and here, are from adducts of sodium, where sodium ions have added to the parent compound. Once you have a material that you want to analyse, obtaining a mass spectrum consists of three main parts. We'll talk here about modern time of flight mass spectrometry, usually abbreviated as TOF and MS. So the three stages. Stage 1 is ionization. Stage 2 is separation. Of the charged particles. I should say here that ionization is adding a charge to the particles. And 3 is detection of the charged particles. We will briefly look at two ionization techniques, although there are several others. One is electroionization, and the second one is electrospray ionization. In electron ionization, the sample must first be evaporated. That is conversion from a liquid or solid into a gas. It is injected at a high temperature into the ionization chamber, which is under a very high vacuum. The gaseous particles are then bombarded with a beam of high energy electrons from an electron gun. This process knocks electrons off some of the particles, generating ions. This suits small, volatile, and ideally fairly robust small molecules and atomic materials. Conversely, electrospray ionization is much gentler, not involving such harsh conditions. It is generally used for larger, less volatile, and often much more fragile molecules. The sample is dissolved in a suitable volatile solvent. You will hear this repeatedly in higher level chemistry. Hydrogen ions are called protons, or referred to as protons. That is exactly the same as a proton subatomic particle. A hydrogen atom has one proton and one electron. If I remove the electron to make an H plus ion, I'm left with a proton. So solvent often has hydrogen atoms which can form protons. These are called protic solvents. If not, something can be added to as a source of protons, or often a source of sodium ions is used instead. The ionization process can then be described as or M plus Na plus goes to M Na plus, where M is the analyte molecule that you're looking at. The sample in its solvent is converted to a spray of very fine droplets, or nebulized. This is done by pumping it through a heated and charged capillary tube into the ionization chamber. The solvent starts to evaporate, leaving charged species, some of which will be M plus H ions in the gaseous phase. So the solvent These are extracted through a plate with a tiny hole in it, leading to a high vacuum chamber. So let's draw a picture. Here is a tube. This is the cone. So we inject the sample plus the solvent into the ionization chamber. Where it forms a mist, very fine droplets. So the cone is usually around about 4,000 volts potential difference, and this this here is the ionization chamber. Over here on the other side of the ionization chamber is an extraction electrode. So for positive ion mass spectrometry, this would be held at roughly minus 50 volts. So some of these particles, solvent evaporates away, minus solvent, leading to the ions of interest, and some of these pass through here into the high vacuum area of the spectrometer. The ions generating, now needing to be separated and detected, are accelerated into the field-free drift zone of the machine, which is a tube with a detector at the end. Enter this so that all the particles have the same kinetic energy. As charged particles, they are subjected to an electric field which gives them an amount of potential energy given by potential energy equals QV, where Q equals the charge particle, V equals voltage applied. The potential energy is converted to kinetic energy, which is given by the equation kinetic energy equals half m little v squared, where m equals mass of the particles and little v equals velocity. Small v can be expressed in terms of the distance travelled and the time it takes. So the velocity can be expressed in terms of the distance travelled divided by the time taken to travel that distance. So small v equals s over t, where s equals the length of the tube and t equals the time it takes the particles to travel that length. So adding this term for V into our kinetic energy equation, we get kinetic energy equals half m s over t squared. This can be rearranged to t equals s square root of m over 2 ke. So here, right, s is the length of the tube, and all the particles. So this is 2, not a z. 2. All the particles have the same kinetic energy when they enter. So S and 2 and Ke, the kinetic energy, is the same particles. So T is proportional to the square root of m. That's is proportional sign. It doesn't equal the square root of m. It equals that. It's proportional to the square root of m. Lighter particles arrive first at the detector and the heavier ones later. We can replace kinetic energy with QV, where Q is the charge and V is the voltage. The equation then becomes T equals S square root of M over 2QV. Now remember, Q equals the charge of the particles, and V equals the voltage applied. So we can see that T is proportional to the square root of M over Q, which is the same as proportional to the square root of the mass to charge ratio, or M over Z, which is the horizontal scale of the mass spectrum. A small point to note: an ion, the mass of 40 and a 2+ charge will arrive at the detector at the same time as an ion with a mass of 20 and 1+ charge. So a 40 mass 2+ is equivalent to a 20 mass plus. Now, the electrospray is a continuous process. The sample plus solvent are pumped into the machine at a constant rate. In order to get accurate flight time measurements, particles must be induced to fly at the same time, separated along their flight path, and then detected, arriving at the detector. When the particles which are charged hit the detector, since they are positively charged, are able to accept an electron from it, generate a current. This is measured, the magnitude of the current being proportional to the number of particles hitting. So let's try to illustrate this with a diagram. Here I have my ionisation chamber. So into here I am injecting sample plus solvent. Here I have my long tube, and here is some form of detector, and this needs to be attached to some form of recording device. I'll just draw a dial here. So this is the recording device. Detector. This is the field-free drift zone. Zone of the machine. I'm going to draw in this is a plate, a charge plate. So in the ionisation chamber I have my fine mist of particles. So it's a fine mist of droplets. The solvent's evaporating away from these, leaving some positively charged ions that will be my M plus H species. Now, if I turn this plate, like the current on in this charge plate, then these ions in here suddenly have potential energy, and they'll accelerate towards the plate, which is negatively charged, and the potential energy here becomes kinetic energy here. Oh, so some of these ions pass through the hole and on a trajectory towards detector. So we have larger particles, so these particles are very small here. The smaller particles move faster and therefore they hit the detector first. So ions separate down the tube depending on their mass to charge ratio. Typically, a pulse of ions will be generated, and the time taken for each size of ion to reach the detector will be recorded. Then the process is repeated until a spectrum is built up. So it's a spectrum of the contents, really, of the ionisation chamber. So that's a summary of how time-of-flight mass spectrometry, especially with electrospray ionisation, works. So this is the end of part 1 of this lesson. Perhaps it's time for a well-earned break. We have looked at or summarised what mass spectrometry is, and how it works. In the next video, part 2, we'll look at some of the kinds of problems that you may come across in an exam context. So, thanks for listening.